Some years ago, I had the opportunity to work in the Galapagos and study Galapagos land iguanas on the island of Santa Fe. This is an adult male, and this is an adult female, and they're quite a bit smaller. Part of my study was looking at how these animals cope with the differences in the seasons in Galapagos. There are two main seasons in Galapagos, separated by some sort of transitional periods in between. In June, July, and August, there's a season that's called the Garua season, and Garua is Spanish for mist. As you can see here, a fog or a mist is rolling in. Although the air is often humid during this season, there's very little accumulated rainfall, and as you can see from the shrubs in this slide, they respond by dropping their leaves during this, what is effectively a dry season, even though the air is sometimes humid. This is contrasted by the rest of the year, which is a much warmer and much wetter season, or the wet season. So after the first rains, literally just after a couple of days after the first rains, these shrubs got leaves and flowers, and so the herbivorous land iguanas had a lot more food available to them during this period. One of the seasonal differences I noticed was the fact that their body temperatures were different in the two different seasons. As you can see, the red line represents the warm, wet season. The body temperature is up around 36, 37, but during the middle of the day. But in the cool, dry season, they're much cooler, 4 or 5 degrees cooler in the middle of the day. So the question is this just simply a result of the fact that the season is cooler, or are they actually thermoregulating at a lower body temperature? Now, in order to answer that question, I used what is called biophysical modeling, and I won't go into great detail about it here, but just to say that we measured the microclimate and put that into an energy balance model and predicted what the body temperatures of the animals would be if they stayed in the coolest environment, that is in deep shade all day, or in the warmest environment, that is out in the sun. This graph shows the simulations for the warm, wet season. First of all, the black line represents the measured body temperatures, the real body temperatures. The blue line shows the body temperatures that those animals would experience if they spent all day in the shade. And the red line indicates the body temperatures that the animals would achieve if they spent all day out in the sun. As you can see, they would get very hot, in fact lethally hot, if they stayed out in the sun all day. This is not a surprise for the warm, wet season. The real question is, what do they do in the cool season? And as you can see, it's a similar result. The black line shows is several degrees cooler than in the wet season, and it's very close to the predicted minimum temperature, that is the body temperature that the animals would achieve if they stayed in the shade all day. The red lines, if the animals were out in the sun all day, still get quite warm. So out in the sun, the animals could get much warmer than they in fact do. So this means that there is a seasonal shift in the behavior of the animals, so that they're selecting microenvironments that allow them to achieve lower body temperatures in the cool Garua season as compared to the warm, wet season. So at the time, there were a couple of possible explanations for this. One explanation that we came up with was related to the fact that there was less food around in the cool season. The other was the possibility that maybe there was some advantage to maintaining as stable a body temperature as they possibly could. But luckily, I had the opportunity years later to study this phenomenon in a different animal and was able to come to what I think is a clear answer to that question. So years later, when I moved to the Northern Territory, I had the opportunity to study this magnificent lizard, the frillneck lizard. These animals are insectivores, not herbivores, but they live in a very similar environment in tropical Australia, that is the wet, dry tropics. Similar in the sense that there's a cool, dry season and a warm, wet season. The dry season doesn't have the garua like Galapagos, but the temperatures are very similar, and also the food availability, because in the cool, dry season, not only are a lot of leaves fall off some of the plants, and the plants look much more desiccated, there are many fewer insects, a lot fewer insects, a lot less food available for the frill-neck lizards in the dry season compared to the wet season. So the other thing that people notice very quickly in northern Australia is that in the dry season, the frill-neck lizards sort of disappear. They're very conspicuous lizards in the wet season, but they're very rarely seen in the dry season. As it turns out, they're just up in the same trees, but just that they inhabit all year round, but they go up higher and they rarely come to the ground. So this graph shows the body temperatures of the frill-neck lizards on the purple line in the wet season, and the two extreme body temperatures, assuming they're in the shade all day, or that's the blue line, or assuming they're in the sun all day. As you can see, the purple body temperature is up around 37, 38 degrees in the wet season. But if they spent all day out in the sun, they could get much hotter. In fact, they would get too hot. But there's no surprises here. So the real question is, what happens in the cool, dry season? This graph shows, again, the purple line, the real body temperatures of the lizards, are several degrees, 4 or 5 degrees cooler in the dry season and in the wet season. And the fact that there's a lot of space between the purple line and the red line indicates that if they wanted to, if they spent more time out in the shade, they would get out in the sun, they would get much warmer than they in fact do. So we were able to watch, once we found out where the animals were by radio telemetry, we were able to watch them throughout the day during the dry season. And what they do is more or less spend the whole day rotating around the trunk of the tree, staying in the shade, mostly in the shade. And so they are behaviorally thermoregulating at a lower body temperature. Now luckily, I was able to study frill-neck lizards for a much longer period than I was able to study land iguanas, and we studied other aspects of their behavior and physiology. And one of the aspects that we measured was their metabolic rate, that's shown in this graph. So this is a graph of the body temperature against the log of the oxygen consumption, which is a measure of how much energy the animals are using. So because it's on a log scale, what's normally a curved line becomes a straight line. And as you can see, as body temperature increases, metabolic rate increases. That's no surprise. That occurs for any cold-blooded animal or ectothermic animal. So as they get warmer, the metabolism goes up. What's different about this graph is that there are two lines. One line on the top representing the wet season, the metabolism in the wet season, and then the lower line representing the metabolism during the dry season. So it's a little bit difficult to interpret because it's on a log scale, but I can tell you that the difference between those two lines is about 30%. So what's happening here in the dry season, the animals have a physiological shift. They have what's called metabolic depression, and their metabolic rate is lower in the dry season than it is at a given body temperature than it is in the wet season, and that results in about a 30% energy savings. So what you see here in this graph, there are two energy savings. First of all, for the one I just described, that during the dry season the animals are on the lower line, saving because of some shift in their physiology. They're saving about 30% of their metabolic energy, but also they're behaviorally thermoregulating at a lower body temperature, which also results in a significant energy savings. So there's physiological adaptation and a behavioral adaptation, both of which allow them to save energy during a season when there's very little food around for them to eat. So the question then is, do land iguanas have a similar metabolic shift? I would hypothesize that they probably do, but that's work for someone else to do in the future.